There is no global now. Ordering events without a shared clock, the capstone of the time stack. Two clocks, both synced via NTP, both as right as a clock gets. Event A reads 0.412, event B reads 0.410, and yet you cannot say which came first. Back at layer 4, we said NTP only ever gets you close, never exact. This is the leftover. A swarm of clocks, each within a few milliseconds of the truth, none of them on it, and no two of them agreeing. That gap is clock skew. Two servers, each with a few milliseconds of uncertainty. The real gap between the events is smaller than either error bar. When skew is bigger than the gap, the order their timestamps give you can be backwards. A better crystal does not save you. So the field makes one move. It stops asking the clock for a time and asks a different question entirely. Not when, but in what order. And you can answer that without a clock at all. Leslie Lamport, 1978. Event A happens before event B only if you can trace a path. Earlier on the same machine, or A sent a message B received, or a chain of those. No clock anywhere, just cause and effect. And here's the part people miss. If no chain links two events, neither happened before the other. They are concurrent, and that does not mean at the same time. It means causally unrelated. A partial order, not a line. Pin a counter to it. Tick up on every event. On receive, jump past the sender's value. That's the Lamport clock. The guarantee, if A happens before B, A's number is smaller. Causes always get lower numbers than effects, a consistent order built with arithmetic. Be precise. The arrow runs one way. If A happened before B, its number is smaller. Yes. The converse is false. A smaller number does not prove A happened before B. Lamport gives you a total order to break ties with, but it cannot tell you whether two events were truly concurrent. Vector clocks, Fidge and Mattern, late 1980s. One counter per process. Bump your own slot on each event. On receive, take the max of each slot. Now the timestamps encode causality exactly. A happens before B if and only if A's vector is less than B's, slot by slot. Here's the prize Lamport couldn't give you. When neither vector dominates, each is ahead in some slot, the two events are provably concurrent. Not a guess, read straight off the timestamps. This is how a version vector data store knows two writes conflicted rather than one following the other. Logical clocks throw real time away. Google's Spanner, OSDI 2012, took the opposite bet. Keep real wall clock time across a planet-spanning database, but be brutally honest about how unsure you are of it, and build that into the clock's API itself. Instead of returning an instant, TrueTime returns an interval, earliest and latest, guaranteeing the true time is somewhere inside it. The width is uncertainty, made explicit. It grows between syncs and snaps narrow at a GPS or atomic reference. Small, single-digit milliseconds, but never zero. When two intervals overlap and you genuinely can't order them, you wait. Spanner deliberately pauses, commit wait, until the transaction's timestamp is safely in the past everywhere, then makes it visible. It spends real latency to buy a real global ordering. TrueTime pays for time in milliseconds on purpose. And that's the one line to carry out of here. Both answers, logical clocks and TrueTime, admit the very same thing. There is no shared exact instant every machine can read. There is no global now. You order with logic or you measure uncertainty and wait it out. No third option. Eight layers ago, this was a single crystal vibrating tens of thousands of times a second, already slightly wrong. Here at the top, it's a planet's worth of machines agreeing on an order without ever sharing a higher now. That climb is the time stack. A timestamp was never a fact. It was always an agreement. Time is a stack, not a number.